Welcome to the Deep Dive. This is where we take your source materials, really get stuck into them, and pull out the key insights for you.
Basically trying to save you some reading time while digging into some fascinating topics.
Exactly. Think of it as your shortcut to being well-informed. Today, we are plunging headfirst into the really dynamic world of coastal landforms.
Yeah, that line where the land meets the sea, it's definitely not static. It's always moving, always being reshaped, constantly.
Absolutely. And our source material for today's deep dive, our guide, if you like, is an excerpt from Certificate Physics and Human Geography, Indian Edition 1-1 by Goat Cheng Liang.
Right, it's a classic text. Really lays out the basics of the forces at work and the features they create along coastlines. Very clearly explained.
It is very clear. So our mission today, unpack the core ideas about coastal erosion and deposition too. Figure out what shapes they make and how this source classifies the different types of coasts we see.
And there are some pretty eye-opening numbers in here about wave power. Plus, the descriptions of how things like stacks and fjords form, well, they really paint a picture.
Okay, let's get into it then. The very first point the source makes, and it's crucial for everything else, is that the coastline is not fixed. It's changing day by day, hour by hour. What are the main things driving this change?
Well, the big three are waves, tides, and currents. Now, tides and currents, they're definitely important. Tides affect that whole zone between low and high water.
Yeah, where the land gets alternately wet and dry.
Exactly. And currents are key for moving stuff around, the debris. But the source really singles out waves as the most powerful agent, especially when it comes to sheer destructive force.
And it gives some pretty wild numbers on that, doesn't it? The actual force hitting the coast.
It really does. It brings home just how much power we're talking about. The text says even average storm waves on the Atlantic coast exert something like 600 pounds per square foot in summer.
600 pounds per square foot. So it's like a couple of people standing on every single square foot.
Pretty much. And then in winter, it doubles.
Doubles to 1,200 pounds.
1,200 pounds per square foot. That's getting towards the weight of a small car on that same area. And that difference between summer and winter, it tells you something about seasonal storm energy.
But that's still just the average storm wave.
That's the key word, average. Because the really big ones, the major storm waves, they can hit with up to 6,000 pounds per square foot.
6,000. That's 3 tons.
3 tons per square foot.
Wow. It's almost hard to picture that much force concentrated right there at the water's edge. No wonder the text says waves like that can just obliterate sea walls, buildings, and chew away cliffs.
Absolutely. It's not just gentle lapping, it's immense pressure. And like you said, tides and currents are still players. Tides expose different parts of the cliff base or shore platform to that wave attack at different times.
Right, like setting the stage differently throughout the day.
Precisely. And currents, they act like the cleanup crew, or maybe the delivery service. They sweep away the eroded bits, silt, sand, gravel, and move them along the coast.
So the currents can actually take the eroded material and use it somewhere else. Or maybe even arm other waves.
Both, yeah. It's all connected. Waves break things down, tides manage the attack zone, and currents move the debris. It's a system.
Okay, so that's the big picture. How does this erosion actually happen, at the rock level? This is where the source gets really interesting, breaking down the specific ways the ocean wears away the land.
Yeah, it goes into the 4 main mechanisms of marine erosion. But first, it explains a bit about the waves themselves, how they start way out in the open ocean. Just the wind sweeping over the water, creating swells.
Just wind, that creates all that power.
Mm-hmm. And a typical wave out there, not a storm wave, might be, say, 20 feet high from the bottom of the trough to the top of the crest.
Okay, the vertical bit.
Right. And maybe 400 feet long between crests. That's the horizontal distance.
That's still a big chunk of water moving even far offshore.
It is. But things change dramatically when that wave gets close to shore into shallower water. It starts to slow down because of friction with the seabed.
It feels the bottom.
Exactly. And as it slows, the wave front bends. It refracts.
Refracts, like light bends through glass.
Sort of, yeah. It bends to align more with the shape of the coast. You can see it if you watch waves entering a bay. They seem to wrap around the headlands. And this bending is really important because it concentrates the wave's energy on those headlands.
So the sticky out bits get hit harder.
Precisely. And the energy gets spread out, dispersed in the bays. That's key for why we get capes and bays later on.
Okay, refraction. Got it.
Yeah.
So the wave bends, slows down, then what?
Then, as it gets really shallow, right near the beach, the top of the wave is moving faster than the bottom. It gets unstable, curls over, and breaks. Crashes down in a mass of foam. That's your breaker.
And that's where the massive force hits the land.
That's the moment of impact, the energy transfer, and the water that rushes up the beach after the break.
The swash.
That's the swash. The source says it's the swash that throws rocks and debris against the land. Really important for erosion.
Okay, swash goes up. What about the water going back down?
That's the backwash. Equally important. It pulls material away from the shore back towards the sea.
And there's one more current mentioned, the undertow. Is that the same as backwash?
Similar effect, but the source describes undertow as more of a bottom current flowing away from the shore. It also helps pull finer stuff back out. Can be dangerous for swimmers too, of course.
Right. So with all that going on, breaking, swash, backwash, undertow, refraction, how does the land actually get worn away? What are the ocean's tools?
Well, that wave action powers the four main processes the source details. First up is corrasion, or sometimes called abrasion.
Corrasion. Sounds like corrosion, but with an A. Does it mean grinding?
Exactly. Think of it like sandpapering, but on a massive scale. The waves aren't just hitting the land with water. They pick up rocks, pebbles, sand. The source calls them armaments.
Armaments, like weapons.
Yeah. The swash picks up these armaments and hurls them against the base of cliffs or grinds them across shore platforms. It wears the land away using its own broken bits.
That's kind of brutal, using the cliff's own debris against it.
It's very effective. And speaking of those broken bits, the second process is attrition.
Attrition. That sounds like things wearing each other down.
Perfect. While corrasion is the rocks wearing down the coast, attrition is the rocks wearing down each other. As the waves move them around, swash, backwash, currents, all those pebbles, bits of shingle, sand grains, they constantly collide. They grind against each other.
Ah, like a giant natural rock tumbler.
That's a great way to put it. This constant bumping and grinding breaks them down into smaller and smaller pieces and makes them rounder and smoother too.
So that's how you get from jagged rocks falling off a cliff to the smooth sand on a beach.
That's a huge part of it, yeah. Attrition is the key process for breaking down larger fragments into finer sand and silt.
Fascinating. Okay, so corrasion grinds the land, attrition grinds the tools. What's number 3?
Hydraulic action. This one's purely mechanical, and it's incredibly forceful, especially where the rock has cracks or joints.
Okay, how does that work?
When a wave surges into a crack or crevice, it doesn't just fill it with water. It traps air inside and compresses it under huge pressure.
Like forcing air into a tiny space.
Exactly. Then when the wave pulls back, the pressure is suddenly released.
And the trapped air expands violently.
Bingo.
It expands explosively. This blast of air widens the crack, loosens rock fragments, wave after wave. This constant compression and explosive release just pries the rock apart.
Wow. Like a jackhammer effect, but using air and water pressure. Must be really effective on cliffs with lots of fractures.
Definitely exploits existing weaknesses. And the last one is solvent action.
Solvent. Sounds chemical. Dissolving things.
It is. This one's most noticeable on limestone coasts, the source says. Seawater contains dissolved CO2, making it slightly acidic, a weak carbonic acid. Over time, this weak acid can actually dissolve the limestone rock.
Like acid rain on statues, but in the sea. Pretty much the same principle. Chemical weathering. The source does add that while it's most obvious on limestone, other rock types can also be weakened or altered by chemical reactions with salt water over long periods.
Okay, so we've got physical grinding with armaments, corrasion, the armaments grinding themselves down, attrition, the explosive air pressure thing, hydraulic action, and chemical dissolving, solvent action. That's quite a toolkit the ocean has.
It really is. It's a combination working together, attacking the land in different ways. And the result of all this erosion is the creation of some really distinctive coastal landforms.
Right. Let's talk about those. The coastal features of erosion. What shapes does the sea carve out? First up in the source, capes and bays.
This comes straight from that idea of differential erosion we touched on with refraction. Coastlines aren't usually made of uniform rock. You have harder rocks and softer rocks all mixed together, often in layers or bands.
So some bits wear away quicker than others.
Exactly. The waves, especially with that concentrated energy on the bits sticking out, will erode the softer rocks like clays or shales much faster. Where you have these softer rocks, the coastline gets eaten away inwards, forming bays or smaller inlets called coves.
And the harder rocks just resist better.
They do. They stand firm, resisting the erosion, and end up projecting out into the sea as headlands or capes.
The source gives that classic example from Dorset in England, right?
Yeah, Swanage Bay is the eroded softer rock, and Durlston Head is the resistant limestone headlands sticking out right next to it. The diagram, figure 74, shows it clearly how the different rock bands lead directly to that jagged, irregular coastline shape.
It's like the geology is laid bare by the sea. Okay, next feature. Cliffs and wave-cut platforms. We see cliffs everywhere.
Right, those steep, often vertical rock faces right by the coast. How fast a cliff retreats inland depends hugely on the rock type, how hard it is, how it's structured with joints and layers, and of course, how strong the wave attack is.
And the waves hit hardest at the bottom, you said.
Right at the base. That's where corrosion, hydraulic action, all that energy is focused. The source shows in figure 77 how this often carves out a notch, or maybe even starts a small cave right at the high tide level. It undercuts the cliff face.
Undercutting. So eventually the rock above just can't support itself.
Exactly. It gets weaker and weaker until gravity takes over and the cliff face above the notch collapses, often in big rock falls. Then the process starts again on the newly exposed cliff face. Undercut, collapse, retreat, undercut, collapse, retreat.
And as the cliff moves back, it leaves something behind.
It leaves behind the wave-cut platform. This is that fairly flat, gently sloping, rocky surface you see at the base of cliffs, often exposed at low tide. It's basically the footprint of where the cliff used to be.
So that flat, rocky bit stretching out at low tide is evidence of the cliff having retreated.
Precisely. It's also called an abrasion platform. The debris from the cliff collapse gets ground down or washed away by the waves, may be deposited further offshore on what's called an offshore terrace.
The source mentions some famous cliffs.
Yeah, the chalk cliffs of the English Channel Beachy Head, which it says is 500 feet high, the Seven Sisters, the cliffs of Dover, about 300 feet, iconic landscapes formed by this process.
They really are. Immense features.
And it also adds an interesting point about how the dip of the rock layers affects cliff stability. If the layers slope down towards the sea, figure 75, the cliff might be more resistant.
Because the layers are sort of leaning against the sea?
Kind of, but if the layers dip inland, away from the sea, figure 76, it's much less stable. Undercutting the base can cause whole slabs of rock to slide down along those bedding planes. Makes retreat potentially much faster. The source shows a photo of a wave-cut platform in Hong Kong, too.
That makes sense. The structure really matters. Okay, what about those classic postcard features? Caves, arches, stacks, and stumps. They often seem to go together.
They absolutely do. They often form in sequence, usually on those resistant rock headlands we talked about, where wave energy is focused. The waves attack lines of weakness joints, faults in the headland rock.
So they find a crack and start drilling.
Pretty much. Hydraulic action and corrosion are very effective at widening these weaknesses at the base of the cliff, excavating holes which become caves. Figure 78 shows this nicely.
Okay, so you get a cave. How does that become an arch?
Well, if caves start forming on both sides of a narrow headland, maybe attacking the same line of weakness from opposite directions, eventually they might erode right through and meet in the middle.
Punching a hole right through the headland.
Exactly. That creates a natural arch. The sea can flow right through it. The source mentions one near Wick in Scotland and shows a diagram of a typical arch.
Arches look amazing, but also kind of unstable. What happens next?
They are inherently unstable. Erosion continues, attacking the sides and, crucially, the roof of the arch, widening it. Eventually, the roof becomes too weak to support its own weight, and it collapses into the sea. Leaving an isolated pillar of rock standing offshore, completely detached from the headland. That's a stack.
Like the famous Old Man Ahoy.
That's the classic example the source uses. Off the Orkney Islands in Scotland, it says it's 450 feet high, a dramatic landmark showing where the coastline once reached. Stacks are common in exposed, rocky places like the Outer Hebrides, too.
And the stack isn't the end of the story either, is it?
Nope. The sea keeps attacking the base of the stack. Corrosion, hydraulic action, they continue to wear it down. Over time, the tall stack gets shorter and shorter until it's just a low, rocky outcrop, maybe only visible at low tide. That's a stump.
Wow. So it's a whole life cycle. Crack, egg cave arch, Kazaki stump, all carved by the sea. What about geos and gloops? Those names are less familiar.
They're related to erosion working upwards, vertically, as well as horizontally. A geo develops when marine erosion, especially working along a major vertical joint or fault line, carves out a narrow, steep-sided inlet or creek right into the cliff face. Think of a deep, narrow gash cutting inland from the sea.
So not just caves at the base, but narrow inlets cutting down from the cliff top, almost.
Or rather, erosion working up from sea level along a vertical weakness. Figure 80 shows a geo near Duncansby Head in Scotland. And a gloop is even more dramatic. It's also known as a blowhole.
Blowholes, I've heard of those, where water shoots up.
Exactly. If you have a cave and there's a vertical shaft or joint leading from the roof of the cave right up to the clifftop surface, when a powerful wave surges into the cave, it compresses the air and water trapped in that shaft incredibly forcefully.
Like a piston.
Precisely. The pressure forces spray, and sometimes solid water, violently up the shaft and out of the hole on the cliff top. Often makes a loud roaring or gurgling noise, too. That's a gloop, or blowhole. Pure hydraulic action at work. Figure 79 shows one at Holborn Head.
Incredible. The variety of features just from waves hitting rock is amazing.
Yeah.
So that covers the destructive side, the carving and wearing away. But you said the sea also builds.
Absolutely. It's not all destruction. All that material eroded from cliffs and ground down by attrition, the sands, the gravel, the shingle, it has to go somewhere. The sea transports it and deposits it, building up new landforms. It's a constructor as well as a destroyer.
And where does it tend to drop this material?
Generally in lower energy environments, places where the wave action is less powerful, allowing the sediment to settle out. Sheltered bays are classic examples, or the areas behind headlands where the water is calmer.
Okay, and how does the material get from A to B?
Yeah.
From the eroding cliff to the sheltered bay?
The main mechanism for moving sediment along the shoreline is a process called longshore drift. The source calls it the most dominant form of transport along the shore.
Longshore drift. Okay, how does that work exactly? It sounds important for deposition.
It happens because waves very often approach the beach at an angle, not straight on. This is usually due to the prevailing wind direction. So imagine a wave hitting the beach slightly sideways.
Right.
The swash, the water rushing up the beach, carries sand and pebbles up the beach at that same angle, diagonally.
Okay, up diagonally.
But then the backwash, the water flowing back down, tends to follow the steepest slope, which is usually straight back down towards the sea, perpendicular to the shoreline.
Ah, so up at an angle, back straight down.
Exactly. So any single grain of sand or pebble gets moved in a little zigzag pattern with every wave. Up diagonally, back straight. Up diagonally, back straight. Over thousands of waves, this results in a net movement of material along the coast in the direction the waves are generally coming from. Figure 81 in the source shows this zigzag perfectly.
That's a really clear picture. It's not just drifting randomly. It's a specific repeated movement. So when this longshore drift carries material into those calmer sheltered areas, what does it build?
It builds constructional landforms, and the most common one, the one everyone knows, is the beach. Yep. The source calls beaches the most dominant form of constructive work by the sea. They're essentially just accumulations of sand, gravel, shingle, whatever material is being transported, deposited where wave energy allows it to settle. Beaches are super dynamic, constantly changing shape and size with tides and seasons.
Okay, beaches make sense. What about spits and bars? They seem more deliberately built.
They are. A spit is a ridge of sand or shingle built out from the land by longshore drift, extending into open water like across the mouth of a bay or a river estuary. Figure 82 shows how one develops.
So the longshore drift is carrying material along the coast, and then the coastline suddenly turns or stops, like at a bay entrance, and the drift just keeps going straight.
Pretty much. The current carrying the sediment continues out into the deeper or calmer water, loses energy, and drops its load, building that ridge outwards.
And what makes it a bar instead of a spit?
If the spit grows long enough to stretch completely across the mouth of a bay, connecting one side to the other, then it's called a bar. A bar essentially walls off the bay or partially walls it off.
Right. And sometimes spits have a curve on the end, a hook.
Often they do, yeah. A recurved spit. The outer end bends back towards the land. The source suggests this could be due to wave refraction bending waves around the spit's end, or maybe opposing currents or secondary winds pushing the tip inwards.
Any big examples mentioned?
A really striking one. Chesil Beach in Dorset, England, described as a shingle bar over 16 miles long, and it connects the Isle of Portland to the mainland.
16 miles, connecting an island. Is there a special name for that?
Yes, when a spit or bar connects an island to the mainland or even to another island, it's called a tombolo. Chesil Beach is a huge classic tombolo. The source also notes that bars can trap water behind them, forming lagoons. Gives the Baltic coast of Poland and Germany as an example where this is common.
So deposition can create new land and new bodies of water like lagoons. What about sand dunes? They're coastal, but seem more related to wind.
They involve wind, definitely. But the sand itself comes from the sea's deposition. Marine dunes form inland from the beach. You need a good supply of sand deposited on the beach by waves and longshore drift. Then, when the sand rise at low tide, onshore winds can pick it up and blow it further inland.
And it just piles up.
It piles up when the wind hits an obstacle, vegetation, driftwood, anything that slows it down. That starts a small dune. Then, specialized plants like marram glass, which can handle the salty, sandy conditions, colonize the dune. Their roots help bind the sand, and the plants themselves trap more windblown sand, allowing the dunes to grow much larger, forming extensive dune belts.
The source gives a massive example, right?
The lands of France, 6,000 square miles of dune landscapes behind the coast. It also mentions dune coasts in Belgium, Denmark, the Netherlands, highlighting that humans often have to work hard planting grasses to stop the sand migrating too far inland and covering farmland or towns.
Wow, 6,000 square miles. That's incredible. So deposition involves the sea bringing the material, and sometimes the wind takes over to build features like dunes further inland?
Exactly. It shows the scale and the interplay of forces. Now, beyond these features formed by day-to-day processes, the source also looks at the bigger picture, classifying whole stretches of coastline based on major long-term changes in the level of the land relative to the sea.
The major types of coasts. It splits them into two main groups, right? Submergence and emergence.
Correct. Coastlines of submergence are formed when the land sinks, or more significantly in recent geological time, when the global sea level rises. The big example is the end of the last ice age. All that melting ice raised global sea levels by perhaps 300 feet, drowning huge areas of former coastline.
300 feet, that would flood a lot of land. What kind of coastlines result from that drowning?
The first type discussed is ria coasts. These form when rising sea levels flood river valleys. Imagine a landscape with rivers flowing down to the sea, carving out V-shaped valleys with branching tributaries. Now, flood that whole system.
So the sea basically flows up the old river valleys, like fingers reaching inland.
Precisely. The drowned river valleys become these long, narrow, often branching inlets called rias. The higher ground between the original valleys remains above water, forming headlands or peninsulas separating the rias. Figure 83A shows this clearly, the drowned valley system.
What are ria coasts like? Are they useful?
They create very irregular, indented coastlines. The rias themselves are often deep and, importantly, sheltered from the open sea by the headlands. This makes them fantastic natural harbors. The sourceless coasts like southwest England, northwest France, northwest Spain, and Portugal as examples, and major ports like Plymouth, Brest, even New York City are located on rias using those deep, sheltered inlets.
Deep, sheltered harbors sounds ideal for shipping. What about fjord coasts? Also submergence, but different.
Also formed by submergence, yes, but this time it's the drowning of glaciated valleys. During the Ice Age, huge glaciers carved deep, steep-sided, U-shaped troughs, often extending below current sea level. When the glaciers melted and sea level rose, the sea flooded these dramatic troughs.
U-shaped valleys.
So
Much steeper sides than river valleys.
much steeper, often near vertical rock walls, plunging straight into deep water. Fjords are typically very deep, sometimes thousands of feet, but interestingly, they often have a shallower section near the mouth called a sill. This is thought to be a ridge of glacial debris, a moraine left by the glacier as it melted back or met the sea. Figure 84A shows that U-shape and the sill.
Are fjords good harbors then, being so deep and sheltered?
They are definitely sheltered, but the extreme depths, very steep sides limiting land access, and that sill at the mouth, plus potential submerged rocks called skerries, can make navigation and port development challenging. They're characteristic of heavily glaciated regions. Think Norway, the source mentions the Sun Fjord, 110 miles long and 4,000 feet deep. Also British Columbia, Alaska, southern Chile, South Island of New Zealand.
Stunningly beautiful, no doubt, but maybe less practical for major ports than rias.
They present different challenges, for sure. The scale is immense. Okay, next emergence type, Dalmatian coasts.
Dalmatian, like the dogs. Or the place.
The place. This type forms where you have mountain ranges running parallel to the coast, and then the area gets submerged.
Mountains parallel to the sea get flooded. What does that look like?
It creates a very distinctive linear pattern. The ridges of the mountains that run parallel to the original coast become long, narrow islands, also running parallel to the new coastline. And the flooded valleys between these ridges become long, narrow channels or sounds, again, parallel to the coast. The classic example, giving the type its name, is the Dalmatian coast of Croatia on the Adriatic Sea. Figure 85 shows that pattern perfectly, lines of islands and channels all parallel.
Very unique. A whole series of parallel islands and waterways. Okay, the last submergence type. Estuarine coasts.
These are formed when lowland areas, specifically the mouths of large rivers, are submerged. The rising sea level floods the lower part of the river valley, creating a wide, often funnel-shaped estuary where the river meets the sea.
Are estuaries good for ports? I imagine they might be silty from the river.
They can be shallow and silty, yes, but they often benefit from strong tidal currents. The regular ebb and flow of the tide helps to scour out the main channel, keeping it relatively deep and navigable. This makes them great locations for major ports, sometimes quite far inland. Think Hamburg on the Elbe, Buenos Aires on the Plate estuary, or London way up the Thames estuary. The tides are key to keeping these ports accessible.
So submergence gives us these varied, often complex coastlines. Rias, fjords, Dalmatian-type estuaries. Lots of potential for harbors, but each with unique features.
That covers the main submergence types in the source. Now for the opposite, coastlines of emergence.
Right. This is where the land rises or the sea level falls, exposing land that used to be underwater.
Exactly. Former seabed or shoreline gets lifted up and becomes dry land, pushing the coastline further out to sea.
What's the first type of emergent coast?
Uplifted lowland coast. This happens when a gently sloping coastal plain is raised up. Figure 86 illustrates this. You see the old sea level and the new, lower one after uplift.
What would that look like? Would it have cliffs and things?
Probably not dramatic cliffs. Because the land was gently sloping, the newly exposed land is also likely to be quite flat or gently sloping. Features that used to be at the coastline or just offshore might now be found stranded inland. Things like old lagoons, salt marshes, wide mudflats, even old offshore sandbars might now be low ridges some distance from the new shoreline.
So you'd find coastal features, but inland.
Yes, remnants of the old coastline left high and dry. The source gives examples like the eastern USA, eastern Sweden, parts of Argentina. Ports that were once coastal might now be miles inland, needing long dredged channels.
And the other emergent type.
Emergent upland coast. This is where faulting or uplift raises a rockier, steeper coastline. Figure 87 shows this, with an old cliff and wave-cut platform clearly visible above the current sea level.
And the key feature to look for here is
a raised beach. This is the most characteristic sign. It's literally an old beach, pebbles, sand, shells, or an old wave-cut platform now sitting well above the reach of the highest tides. You might see several levels of raised beaches on a hillside, marking different stages of uplift or sea level stability in the past.
So you could be standing on the current beach, look up the cliff, and see a flat terrace with old beach material on it?
Exactly. Clear evidence the land has risen. While geologically fascinating, the source suggests these emergent upland coasts aren't typically as good for ports as other types, perhaps due to the rocky shores and lack of natural inlets. Examples mentioned include parts of Scotland, which has famous raised beaches, and the west coast of the Deccan in India.
Okay, so emergent coasts tend to be straighter, less indented, and might have these fossil coastal features left inland or stranded high up, a very different look from the drowned coastlines.
Absolutely. It really shows how the coast's shape records these huge geological shifts over long timescales.
It's amazing. The coast isn't just about today's waves. It's a history book written in rock and water.
It really is. And, while we focused on waves, tides, currents, and these big sea level changes, the source briefly mentions other factors too.
Like what?
Well, obviously the nature of the rocks themselves, their hardness, how they're layered or fractured, that dictates how easily they erode. Granite versus clay makes a huge difference.
Makes sense. The raw material matters.
And also, the amount of rock exposed, the shape of the coast, and importantly these days, human interference.
Ah, yes. Us building things.
Exactly. Seawalls, groins to trap sand, dredging channels. All these things we do to protect coasts or improve harbors inevitably interfere with the natural processes of erosion and deposition, sometimes with unexpected knock-on effects down the coast.
So pulling it all together, what have we learned from this deep dive into Gocheng Liang's description of coastal landforms?
Well, we've seen the coast as this incredibly dynamic zone, a place where powerful destructive forces, mainly waves using tools like corrosion, attrition, hydraulic action, and solvent action, are constantly wearing away the land.
Carving out features like capes and bays through differential erosion, creating cliffs and wave-cut platforms through undercutting and retreat, and producing that amazing sequence on headlands, caves, arches, stacks, and finally stumps. Plus geos and gloops?
Exactly. But then there's the constructive side. Longshore drift acts like a conveyor belt, moving the eroded sediment along the coast.
Building up beaches, extending spits and bars. sometimes even connecting islands with tombolos like Chesil Beach and supplying the sand for wind to build marine dunes and huge dune belts like the Landes in France.
And we looked at the big picture too, how major shifts in land or sea level create fundamentally different coastlines. Submergence giving us the drowned valleys of Rheas, the deep glacial troughs of fjords, the parallel ridges of Dalmatian coasts, and the wide mouths of estuaries, often great for harbors.
While emergence creates straighter coasts, lifting old beaches and platforms high above the current sea level, leaving former lagoons or mudflats stranded inland.
It really highlights the complexity. The coastline is constantly being shaped by processes acting over seconds like a wave breaking and over millennia, like ice ages ending or continents shifting. And now, increasingly, human actions are part of that mix too.
It definitely makes you look at the seaside differently. Not just sand and water, but a whole geological drama playing out. Okay, here's a final thought for you to take away. We know coasts are dynamic, shaped by nature and increasingly by us. With things like future sea level rise predicted and more development happening right on the coast, how might these incredible landscapes, the cliffs, the beaches, the estuaries we've talked about, change even more dramatically within our lifetimes? What does that mean for the balance between erosion and deposition and for the different coast types we've explored?
Something to definitely keep an eye on as that conversation between the land and the sea continues.